So today I'm going to talk about non-equilibrium Bose-Einstein condensation in variety of settings. And most of these works are done by my PhD student, me, and in collaboration with Sergey and Evgeny Sherman. So I will, just to provide a continuity, I will connect with where Matthew left. So these are some simulations of the rotating quantum turbulence for different aspect ratios as you go from, full 3D box to 2D. But okay, that's not the point of discussion here. Since I've been put in the, turbulence section, so I will take turbulence as a dynamic field that is spatially complex, aperiodic in time, and involves fluctuations that vary across a wide range of length and time scales, because this is going to allow me to cover superfluid turbulence and non-equilibrium condensation, which essentially would be wave turbulence, what I'm going to talk about. So I will be talking about non-equilibrium condensation in 3D system in the presence of forcing and dissipation. And if time permits, I will actually go to 2-dimension and show some results on binary system with and without spin orbit coupling. Okay. So strongly turbulent phase is generally regarded as a dynamic interacting tangle of quantized vortices on top of a condensate and random waves and other coherent structures. So something looking like this. So some time back, we did a large-scale simulation of the Gross-Pitesky equation, okay, and generated a turbulent state starting from some initial condition. So you see a jungle or a forest of vortices, and you can zoom in and you see there are some regions where these come together and form large-scale bunching, and there is a heterogeneity, okay? So you can have rings and so on. So this is a strong turbulent phase. Now if you look at the incompressible kinetic energy spectrum, so at small wave numbers, you will see a 5/3, which is consistent with the classical turbulence. But if you go to higher wave numbers, the wave numbers which are smaller than the, at higher wave numbers, you see Kelvin wave cascade or associated with the Kelvin waves which Matthew was talking about. So if you have larger and larger simulation sizes, you can disentangle variety of collective processes, non-equilibrium processes which are going in the strongly turbulent phase. Okay, from there I will switch gears and come to non-equilibrium condensation. So what I want to essentially convey here, and it's kind of well known, that BEC may occur out of initial states that are far from equilibrium, and this condensation process is strongly non-equilibrium. Moreover, this shares features that are typical or common of turbulent systems like cascade-like transfer of excitations through momentum space, and in the absence of forcing and dissipation, you will have two conserved quantities, that is total energy and the total number of particles, and the situation becomes quite analogous to 2D turbulence, which Guido was talking about. So here you can have a dual cascade. So you will have a non-equilibrium condensation as an inverse cascade of mass or particles in the K space, that is from high wave number to small wave numbers. And then you will have a direct cascade, that is creation of high momentum particles which eventually escape from the trap or from the system. Okay, you will lose them. So what is essentially we are looking for? We are looking for the dynamics of the formation of a BEC and the non-equilibrium setting. We would be looking for universal scaling behavior in the evolving turbulent spectrum. And for simplicity, so as to have low computational cost, I will kill the direct cascade process and I will show how. And this is based on the work that we recently did. So I mentioned wave turbulence, and what do I mean by wave turbulence? An out of equilibrium system of non-linearly interacting random waves, which are characterized by presence of interscale transfer of certain conserved quantities. Okay, fine. So what I'm going to do, I'm going to take my nonlinear Schrodinger equation and brutalize it by including forcing and dissipation. I will show you the form of forcing and dissipation in a bit. So F is going to be the forcing term and D is the dissipation term. And as I was telling you earlier, in the absence of forcing dissipation, the mass and the energy are conserved. Okay, and a few other parameters which are of interest. So there is an energy which is associated with the linear terms. I will call it E2. Then there's an energy associated with the nonlinear terms. I will call it E4. And I will use this to define a parameter eta that will give me a crude sense of how nonlinear my system is. That's going to be very crude sense, but again, the whole talk would be very qualitative. And then, of course, I have my speed of sound defined in terms of alpha, g, and rho, hailing length, okay? Now, if I'm going to introduce forcing and dissipation, what may happen is that the total mass and energy are going to depend on time, especially if I'm not in a stationary regime. Let's say if I want to focus on a non-stationary turbulence, and this is what we are going to talk about here. So, few words on the forcing. We are going to introduce our forcing at very high wave numbers because we are interested in the inverse cascade setup. So, forcing I have in Fourier space, I can write forcing as F naught times exponential of I times theta, where F naught is the forcing amplitude. Okay, and this forcing is active only in a thin shell, okay, between Kf1 and Kf2. Otherwise, it's 0. Okay, so we are in a 3-dimensional setting, and I force a 3-dimensional, I force a shell, and essentially I use this theta as random phase, and this random phase is uniformly distributed between 0 and 2 pi, which are independent at each time step and in each k. Okay, and to maximize the inverse cascade, I'm going to have my forcing at very high wave numbers. For example, if I'm doing 512 cube simulations here, I will be forcing at 131 and 130, a shell between that. Okay, and dissipation at still higher wave numbers is there, and I will kill it by introducing an artificial dissipation mechanism, for example, hyperviscosity. Okay, and what I will get is a non-stationary turbulent state with condensation, and the evolution then is not going to be influenced by dissipation if I tune my artificial dissipation mechanism effectively. Okay. Okay, so now Miguel has already covered it, but I will just quickly go through it for the purpose of my talk. So key player here or key observable here is the wave spectrum. Okay, wave spectrum is obtained by averaging Fourier transform of the wave function over a shell. Okay, and then what I will be doing direct numerical simulations of the Gross-Pitesky equation, and I will be comparing it with some predictions which have been made by the wave kinetic equation. That's one of the goals, not the ultimate goal. So if I want to do that, I will write down the wave kinetic equation. So I will switch from nk to n omega, the way it's usually written, and omega and k are related by this. Okay. And the kernel here is given by this. Okay, we don't have to bother much, but just say that there's a wave kinetic equation, you can solve it, and it will give you some solutions under a variety of settings. So for example, if you are going to look for the solutions of the wave kinetic equation, you have two thermodynamic solutions corresponding to particle equipartition that will tell you omega, n omega is constant. Second is energy equipartition, which is going to give you n omega as 1 by omega. And if you want to convert this back in terms of nk, okay, I think I will come back to it. Okay, that's the two thermodynamic solutions. And you can have non-equilibrium stationary power law, Kolmogorov-Zakharov spectra as well, which Miguel was talking about. So for an inverse cascade, you will have omega as omega to the power minus 7 by 6, and for a direct cascade, you will have omega to the power minus 3 by 5. Okay, so but you can also have non-stationary solutions in the inverse cascade setting, which blows up to infinity in a finite time. That's when the condensate starts forming. I mean, when the front reaches the k equals to 0 mode. But this is preceded by power law behavior omega to the power minus x star, let's say, which is developing in the tail. and then it invades the entire inverse cascade range as you go to this blow up time. So there was some confusion in the literature. Some people said, based on numerical solutions of the wave kinetic equation, that this x star should be 1.23 or 1.24 in between that. And then there were other paper where x star was assumed to be 7/6, which coincides with this, okay, inverse cascade, non-stationary solution. So one of the goal is also to resolve this. But before I can compare my numerical simulations of the Gross-Pitesky equations with the wave turbulence or the wave kinetic predictions, I should keep in mind what are the requirements for the wave kinetic equation. So the first and the foremost requirement is a small nonlinearity. The parameter that I had introduced should be very, very small. Okay. Finite box effect should not be important. And associated K-space discreteness is not important. Okay. But what may happen during the evolution, if the condensate which is forming grows to a large value, it may start to affect the uncondensed wave with K equals to 0. Moreover, if the condensate becomes of the order of 1, then these uncondensed waves can be regarded as perturbations on top of the condensate, and then these waves will satisfy Bogoliubov dispersion relation. Okay. So with that, I will come to the numerics. So I have done 3 runs at 512Q so as to have a decade of inverse cascade so that I can be confident of the exponents, but it turned out to be slightly more difficult than that. So I designed 3 runs. So 3 runs have following value of G. So 14.41, 14.41, 57.41, and then I also started varying the forcing amplitude just to have variety of sets and see what is happening. So now just to compare these runs so that you don't have to carry in your head these numbers. So let me make this small remark which is relative for these 3 runs, is that the last run where G is highest, F naught is high, has the highest initial degree of nonlinearity when I start the simulation. Similarly, if you look at the first one, it is going to have intermediate initial degree of nonlinearity, and the middle one, the run 2, is going to have lowest degree of nonlinearity. Okay. So is it the case? So let's look at the temporal evolution of the nonlinearity parameter. If you look at the nonlinearity parameter, you will see that it falls very rapidly for some initial duration. This is an artifact of the initial condition. Okay. But the moment the forcing starts to dominate, you will see for quite a bit of time, let's say if I focus at 2000, so the nonlinearity parameter for the strongest nonlinear term, that is run 3, which I'm saying has the highest degree of nonlinearity, highest G, even for that, eta is less than 0.2. So even what is my strongest nonlinear run is very weakly, is weakly nonlinear, so I should be in the regime of weak wave turbulence and so on and so forth. But as time progresses, these are non-stationary turbulent states. So you see that nonlinearity of run 3 increases and it becomes 1, and later on we will see that there's a condensate formation and so on and so forth. But if you look at run 2 remains very weakly nonlinear, or eta remains very small throughout. But run 1 also picks up, but again remains very small. Now if you look at the condensate fraction, there's something anomalous happening for run 2. What we see that is there is a significant condensate fraction developing there. Okay, more about this later. But if we look at run 3, slowly the condensate fraction builds up and then it becomes quite significant. Now if I compare it to run 2, which remained very weakly nonlinear, so the puzzling part is how come the condensate fraction is so large. Okay, but run 3, which is this relatively stronger nonlinearity, you see that the condensate fraction is smaller than this. Fine. And run 2, it always remains smaller. Okay. So with that, now let's move to the wave action spectrum, specifically 1D wave action spectrum that I obtained by summing this mod psi k square over a spherical shell and dividing by the thickness of the shell. Okay, I construct this object and I track this object as a function of time for these 3 runs in the early stages, in the late stages, because I want to compare them with these pre-blow up and post-blow up time, like what the scaling is. So if you look at, let's say run 1, you will see that all these runs, in fact, in the very early time, they have k-square spectrum. This k-square spectrum, if you now correlate with this, if you want to see in terms of omega, where x is the scaling which is there, if you write these spectrum in terms of omega, so it corresponds to constant, okay, which is particle equipartition, right? All these 3. But as time evolves, you see that some second scaling region starts to appear on wave numbers smaller than the forcing wave number. Okay, you see here, here, here. And now if you convert them again, you will find numbers which are like 1.29, x equals to 1.29, 1.4, 1.26, which become consistent with what was obtained in the numerical simulations of the wave kinetic equation. Okay. Now, as time evolves further, so something else that I should mention is that there's this vertical line. This vertical line is where I have k roughly of the order of 1 by healing length. Okay. So because on the left to the 1 by healing length, you have stronger effects of nonlinearity. Okay. So now at late stages, if I look at the spectrum, I see that there is a plateau developing. Okay. And that plateau is consistent with the energy equipartition. And then at further small wave numbers, you see the spectrum is peaking near k equals to 0. Of course, in an ideal situation, you will expect a Dirac delta. We are not in an ideal situation. So my condensate is not uniform. Okay. It has space-time variations and some other coherent structures in it. And this is also close to, if you want, close to k minus 3, which in some works of Boris Novak and Sexty and Thomas Gassenger, they, in their 3-dimensional wave action spectrum, they write it as, I mean, you will expect a scaling which is k to the power minus 5, but one needs to check further. Okay. Now, if you want to look at the spatiotemporal spectra for the first run, early stages, you will see that you have a spectrum which is consistent with the 4-wave process. So you have these random wave, okay, you have these k square linear. Okay. Now in run 2 also early stages, you see a behavior which is consistent with k square. I'm plotting omega versus k plot, spatiotemporal spectra. Then if I'm at late stages, some condensation I can see here, which was there even at, in the condensate fraction. But if I go to run 3, in the early stages, I again see 4-wave process, k square behavior. But as we enter the late stages, we start to see the condensate appearing. And this condensate appears like a horizontal line here. Okay, so it has some finite k range, and it is situated at some frequency omega. So basically, it's like, as I said earlier, it's not a uniform condensate, and it's like oscillating as a coherent object at some given frequency. Okay. So if I now look at the visualizations of the density for some density isosurfaces, for run 3, you will see that in the late stages, these are for late stages, you begin to see some vortex loops forming, vortices forming, loops forming. Okay, so you see, I mean, these are vortices, and you're already in a, you have a condensate, you have now converted to a 3-stage process. Okay. Similarly, in run 2, you have vortices. Run 1, where the density is very small. You see some vortex-like structures, but these are primarily ghost vortices. So these lines are just indicating regions of zero density. So in summary, we have analysis in the inverse cascade setting, comparison with the wave kinetic equation. We get a scaling which is consistent with 1.23. And consider setups where the applicability conditions for the wave kinetic equations are violated initially or as a result of evolution. That is, the non-linearity of the system in the non-stationary turbulence, keeps evolving. And because of that, you may be in tune with the wave turbulence theory prediction, or you may go out of it. Okay. So now very quickly, I will also just show some plots where I have looked at the phase separation under non-equilibrium conditions in 2-component system. So I will take a binary mixture. I will look at the conservative relaxation dynamics or dynamics in the presence of forcing and dissipation. Again, the focus in these two would be on the non-stationary regimes. And this is so as to just to be in sync with the theme of the meeting, because it's about 2D quantum fluids. And then I will repeat the same in the presence of a spin orbit coupling between the 2 components. And I will just show a very qualitative result. Some of these I produced on Tuesday while sitting at the back of the bench and listening to the talks. So this is going to be my 2-component Gross-Pitesky equation. If I am just still here, I'm describing a binary system. If I include these 2 terms, then I'm describing a spin-orbit interaction. I'm not an expert here, but just for fun, I'm showing you. So G11 and G12, G11 and G22 are the intra-component interactions, which I will label as, in rest of the slides, as G. And interspecies interaction, I will represent them by G12 and G21, which I will take them to be equal for the rest of the studies. And it's very well known that you get phase separation if you have G square is less than G12 times G21. Okay. So what I will do now, I will also do the same, play the same game for spin orbit coupling, but I will kill the Dresselhaus coupling term and keep only the Rashba strength, okay, which I'm going to denote by lambda. So first I will start with conservative dynamics. So there's no forcing, no dissipation. I initialize my wave function in Fourier space at some small initial wave number like a Gaussian there with random phases, and I let the system evolve. I should see the coarsening dynamics or miscibility, immiscibility, depending upon this condition. Okay, so if I'm here, G equals to 1, G1 to 0.5, and lambda 0, the 2 components are are miscible. What is not clear here, I mean, these are the pseudo-color plots of the density of one component, and these lines that you see, they were supposed to be white lines showing the contours of level contours of the second component. So if you see dense lines, you should expect that more density of the second component. Okay. So in these, you see that they're uniformly distributed. So you have mixing or miscibility. Now I will start to introduce lambda. So if I start to introduce lambda, here going from left to right is time for a given lambda for a given value of G in G12. Okay. So for lambda 0.5, I still see miscible behavior. But if I'm at lambda 1, but this condition for a binary condensate, this G and G12, they are telling me that the component should be miscible, but putting this lambda starts to giving me some patterns. Okay. So if I increase this further, I still get patterns, not very clearly visible, but they are forming structures of small size, and I will show why. Similarly, I can play the same game, keep varying G1, 2. I will finish very shortly. And if I increase the strength of the lambda, I start to see pattern. So similarly, I increase it here, further G1, 2, and then I play with the lambda as well. I keep seeing patterns, stripes rather. So even higher value of G1, 2, I will see pattern. Okay. But how robust are these patterns and condensation which is happening if under forcing and dissipation? So here I took the same system, introduced dissipation and forcing in 2D. Okay, what I was describing for the 3D system. And I'm describing component 1, component 2 density, and this is how time is evolving. This is a binary system, no spin orbit coupling. I end up with a phase separated spin. I did the same in the presence of spin orbit coupling. Okay, and I follow the time here. I start to see these stripes. And just to end, yet another simulation with lambda 5. I will show you the spatiotemporal evolution of the density fields. Okay, I think I will have to quickly go in. You see? And below I have shown you the spectrum, 1D spectrum based on psi1 and psi2. I can do the normal mode analysis and plot for the normal modes of corresponding to the 2, and you will see that one of them is showing a strong peak at lambda 5. I think I forgot to include the spatiotemporal spectra, otherwise I would have shown you that for this normal one you see a horizontal streak and a dip where there's a condensation occurring at k corresponding to lambda. I think that's all. Sorry, I kind of rushed through, but it was just to be in sync with the dimensionality of the meeting. Okay, thank you.
To study wave turbulence prediction, wouldn't it be better to have a steady state in the inverse cascade? I mean, I understand that you're interested also in the condensation stage, but
yes, but then there are variety of phases or stages one can be interested in. I mean, you can design an experiment or a numerical experiment where you focus only on non-stationary, but there may be a situation where you're genuinely interested in a non-stationary situation. So we try to, look at the non-stationary case here. Of course, people have looked at stationary cases as well.
Is it working? Yeah. Very nice talk, thanks. In the first part of your talk where you did the 3 runs, I didn't quite get where you had the rather different condensation fraction growth.
Yes.
What the comment was, if you can go back to
that. So that was because of the level of nonlinearity in the different runs were different. And that kind of affected the eventual fate of the evolution. So for this one, it could proceed from 4-wave to 3-wave. You could have a strong condensate and vortices. And for the second one, it got stuck somewhere because what I didn't mention, that the nonlinearity became very weak. So the resonances went down. So the cascade process got inhibited. So whatever got, could make 2D k equals to 0 mode, got stuck there, could not come out of it. Okay, and for the other one,
can you go to the plot actually, the next graph here? Yeah.
So for the run 2, this is what it happened, and run 3, the nonlinearity was decent enough. It took me from the usual stages, and I eventually ended up with a strong condensate with vortices on top of it.
So what happens to the blue and the red curves on the right for longer time?
So the blue one, okay, so I have not run very long. For example, if I look at run 1 is the blue curve. The nonlinearity is slowly growing. But if I run very long, and these are 3D runs, very long runs, with the nonlinearity going down, the process evolves very, very painfully slowly. Okay, so now if you look at here, you see a peak, right? So like here you had a peak, but it kept moving up, the lower modes went up and up. So probably if you run very long, if you have lots of money, then this will pick up and you will have a condensate developing maybe. Yeah. So, but I had to stop there because I had what I wanted from this run. Yeah. Yes.
Okay.
Very nice talk. I have a question because your forcing increases the atom number, right? Constantly.
Yes, yes, yes. So that is not control. It can increase or decrease depending upon the interplay between the forcing and the initial condition I had put. So I'm not bothered at all about conserving the particle number or trying to come in some stationary state with regard to that or even with regard to energy. So I'm just taking some wild situation where the number of particles can keep on increasing, energy can keep varying, and I still look at the cascade which is developing.
Yeah. I'm an experimentalist. I was just looking for more, let's say, a physical situation. Have you considered the forcing that basically you have a condensate initially, you just start forcing at some high K where there is nothing.
So you're
the
starting
atom
with a
number is
situation.
sort of conserved.
Sorry to interrupt. You're starting with a situation where there is a condensate. You're saying.
Yes.
Okay.
And then you force at some scale very high up, and whether you see some inverse cascade dynamics, but with, let's say, atom number conserved. So you always depump the condensate, but because okay, we are doing some similar experiments. That's why I'm asking.
Sorry, maybe, I mean, I'm not getting it completely. I mean, there is a condensate and then I'm forcing at very high wave number.
Yes, and you should still see the inverse cascade, right?
Yeah, you will see the inverse cascade. You will see the inverse cascade, I think.
Yeah, I was just wondering whether you did some kind of simulations like that.
I mean, see, there is a condensate developing here, and even then there is a flux of particles which is going and sitting in the condensate. For example, in this run, in this run, till the time I stopped, condensate has developed. I mean, the situation that you are telling, I will not bother about the scaling or what exactly the process is, but there is a cascade where the particles will be transported in the momentum space from the high wave momentum to the low momentum, even if there's a condensate. At least that's what I can guess from this. Okay. Unless there's some other mechanism which creates a bottleneck. And so did I answer or?
Yeah, more or less, yes. Yeah, thank
and the wild situation could be some astrophysical setting or, I don't know, maybe.
Thanks.
Okay.